Hello, welcome back. We're going to do another example today. So it should be a pretty quick video, just going through this example. It'll be the example on the front page of your assignment. So if you want to go ahead and get that out, we're going to follow through together. I hope you kind of like this new format, something I started last year towards the end of the year, where the example that I go through on the board, you also go through the process of and write in the answers and stuff and fill it out as we go. So you're not just listening to me do something totally different and then you don't have any record of it on your own paper. So the whole front side is going to be the example we do together. Then the back side, we just got a few problems. See, I think we got four problems. Yeah, so we just got 4 problems that you'll do on your own. So here we go. The question that we want to answer is, would you pay a friend more for a used camera than a stranger? So they set up an experiment where they had a used camera that was in good condition, and they asked people how much they would pay for it if it was being sold to them by a friend or a stranger. And so those were 2 random treatment groups, whether or not they asked the person that, and they told them that it was being sold to them by a friend, and another treatment group, they asked them if randomly assigned treatment group, and they said that it was being sold by someone they didn't know. And they listed off all their responses to that question of how much they would offer. So the price offered for a used camera when buying from a friend, here are those values, and here are the other values here. Notice they're not the same exact sample size of people that fell into the 2 different treatment groups. That's totally fine. It just tells us that we'll probably have a different sample size. So the standard deviation sampling distribution model might have a smaller standard deviation because we're dividing by the square root of n. So if we have a larger sample size, then that might come into play. So used camera, so it was the same used camera in good condition, different buying. The only part that was different was whether or not they were told the treatment group of buying from a friend or buying from a stranger. So here are it's kind of hard to see and analyze this data when it's in a list like this. So they graphed it out into, looks like box plots. They're probably modified box plots. We just don't have any outliers, so we can't see that part. So buying from a friend looks like people would pay a lot more money. In fact, the minimum amount they were offering to pay a friend was close to the maximum amount that somebody would offer to pay to a stranger. So it's almost the entire set is entirely above that. And we can clearly see that whenever we graph these parallel box plots right next to each other, just like this. Also, there's a much larger amount of variation in the pricing that was offered whenever we were buying from a stranger. Looks like we got some lowballing going on here. There's also just a whole lot more variation. But when it's being offered what you would pay a friend, it looks like people are not willing to lowball a friend, maybe because they would be embarrassed or something. And it looks like they are all offering kind of a high-end value, high-end towards the fair market value, towards the upper end. Okay, so interesting stuff we can see from just visualizing that data there. So let's go through our assumptions and conditions. So randomization. Now this is an experiment, so as long as the treatment groups are randomly assigned, it doesn't matter if we randomly select the participants. That doesn't matter at all as long as they're randomly assigned treatment groups. Okay, so independent groups. So the 2 groups, they have to be independent of each other for us to be able to do the calculation of adding the variation of the 2 groups for the sampling distribution model, or the difference of the 2. So on this one, so the random assignment makes sure that the groups are independent. So that's totally fine because we didn't let people choose the group that they were in. Then their answers can't be associated between the 2 groups. So we're good to go. Independence. So experiments don't need to be a random sample from the population. So as long as it was a randomly assigned treatment groups, they should be independent of each other. So we're good. Then the nearly normal part, this is where we ask whether or not we believe that the population, which is the group of the set of all offers that we would get from a friend, if we were buying from a friend or if we're buying from a stranger, if we believe that those were nearly normally distributed. Well, we didn't graph out a histogram, but from these box plots, they look like they're symmetrical. They might be slightly skewed from buying from a stranger towards the left, right, the low end. But we would assume that they would be normally distributed. Also, with a larger sample size, we're taking the average of 1, 2, 3, 4, 5, 6, 7, 8, and 7. So with a larger, and I know it sounds small, but this is a larger sample of when we're taking a mean. Even if this is slightly skewed with the buying from a stranger, it's okay because the central limit theorem is going to kick in and make the sampling distribution model become more nearly normal. So the histograms look roughly unimodal and symmetric. I guess maybe we did have histograms, but I was looking at box plots, so I don't know what I was talking about there. All right, so here's our two different distributions with their summary statistics. So the average that we would pay or offer the camera if it was buying from a friend, and the standard deviation, which is much smaller than the standard deviation from a stranger, and this is much more of an offer than the average that we offered the stranger. And the sample sizes of 8 and 7. So to find the standard error for the mean that we'd offer a friend, so I'm just doing sub F for friend and sub S for stranger and color coding it so you can see, as we would take the mean amount, the standard deviation of 18.3 divided by the square root of n, and that's going to give us that value, and that's going to be the standard error for the sampling distribution model of samples of size of 8 with their means. So we would assume that the population would be like our sample, and this would give us our sampling distribution model. Now, typically we do sampling distribution models centered at the actual population mean, but we don't know. So this is really to build a confidence interval, if nothing else. All right, same thing with the stranger. We take our larger standard deviation because there was a much larger variation in offers for a stranger, and then divided by our smaller sample size. So this is definitely going to have a much larger standard error for the sampling distribution model, and that shows up here as well. So much larger standard error for that. All right, so we've got two different things, two different samples, and we want to compare the two means. So the difference that we see in the two means, friend minus the stranger, and I put the friend one first so that our value would be positive, or because we expected the value to be positive. We expect that we would offer a friend more than we would offer a stranger. So the difference was $70.50. Now the question we have is that difference, could that just be based on sampling variation? To be able to answer that question, we have to look at the sampling distribution model for the difference between these two random events. And that has to take into account their individual sampling distribution models variation, right? So let's write our hypotheses. So our null hypothesis is that there's no difference. So this is called the delta naught. So the hypothesized difference, the capital D for delta is like a capital D in the Greek letter or whatever. Greek alphabet. So delta naught is what we usually is always 0. So we almost always hypothesize that the difference between the means is 0. So that there's no difference between the mean price offered to a friend and a stranger. The alternative, we're going to do a two-sided thing saying that there is a difference. If we were interested in one side, we would probably be interested, do we offer a friend more money than we do a stranger? You can argue that, and I totally see that as a valid point as well. All right, so if our null hypothesis is based on there being no difference, then what we would need to do is take the average of both of these and pull them together, but not just take the average, because we have to weight it by the sample size. So we had 8 people who were asked how much they would pay a friend for the camera, and this was their average. So that's going to give us a total amount offered by the 8 people. And then the 7 people that offered this on average, so that'll give us a total. It's kind of like undoing an average. And then we're going to divide it by the total number of people who were a part of our experiment, which was 15. And this gives us a pooled mean of $249. Now, this is fine as long as we have the assumption to pool. We have to have the assumption that they have an equal variance. Now, if we go back to the original samples, did it look like the variation between the two groups? Between the two groups, did they look like they had equal variance? No, we obviously had much more variation in the price offered to a stranger. So it's really not appropriate to do this pooling like we're doing here. So if they were the same and it was 290, then one of those samples was low, what we'd offer a stranger. One of the samples would have been high that we offered a friend. Could those both have just occurred by chance? And that's the question we're trying to answer. So what we need is a sampling distribution model for the sum of the two random events, which would be like the Pythagorean theorem. So we would take the sampling distribution model for the friend and from the stranger, and that'll give us the total for the sum or difference between the two means. So how we do that, again, just like I showed yesterday, notice the friend one's much smaller than the one for the stranger, has a much larger standard deviation for two reasons. The individual sample had a much larger variation or standard deviation, and also it's a smaller sample size. So what we end up doing is just like the Pythagorean theorem, which is so cool. I love doing this. It never gets old for me. And it's if these two are independent of each other, and they are because they were randomly assigned treatment groups, then it's like the Pythagorean theorem where we have a squared plus b squared is equal to c squared when we're talking about their standard deviations. Or in other words, the standard deviation squared, which is the variation, is going to add. So we add the variation in the friends, sampling distribution model from the friends, and the standard deviation, the variation and the sampling distribution model from the stranger, and that'll give us a total variation for the sum or difference between those two. Cool stuff. All right, so the observed difference in the means was $70.50, right? And so basically this is showing the Pythagorean theorem. So what we did is took the variation. So we take the sampling distribution model and square it, and the standard error of this one and square it. And then we add them together and take the square root, and that gives us the standard error for the difference between the friend and the stranger, which would be 18.17, which is what we have here. So we observed a difference of 70, which is way off the charts over here, well above what the other ones were, or well above 2 standard deviations. So it's obviously unusual. Our z-score, or t-score in this case, because we are dealing with means, so we have to use Gossett's family of models with some weird degrees of freedom, is going to be 3.77. So we are 3.77 standard deviations above the mean, which is well beyond what we would consider a usual observation that could occur by just random sampling variation. So to find the degrees of freedom, we don't use 7, we don't use 8, and we don't just subtract 1. We don't add them together to get 15 and subtract 2 or 1 from that. We have to use that nasty formula that comes from the calculator. Boom. Isn't that gross? Let's do it like the sum of the variations divided by like their weighted degrees of freedom sum of the variations. I know it's some funky stuff. Anyway, still haven't wrapped my head around it, but that's okay. So the p-value, when we do that, gives us to be less than 1%, which means the probability of occurring a difference of 70.5 that we found between those two sample sizes and everything like that is less than 1% of the time. So we would assume if there was no difference that the means difference would be 0, and based on their sample sizes and standard deviations or standard errors of their samples and whatnot, we would expect that to occur, a sample difference of 70.5 to occur less than 1% of the time. So for any reasonable alpha level of significance, we can reject the null hypothesis in favor of the alternative. So let me graph it out so you can see what's going on here. So if the difference was 0, then the probability of occurring a difference of 70.5 would be p-value of 0.6%, which is very, very unlikely. Now, the first thing we do is we set our alpha level of 10, 5, or 1%. Now, our default is 5. If you're talking about candy, we do 10%. Something doesn't matter, right? If something life or death, like death row or something, or life in prison, then we're going to set a really strict burden of proof. In this case, we're talking about something's not really that important, but we'll just keep it at the default of 5%. All right, so 5% alpha level, which means 5% of our samples, if this was actually true, where there was no difference, delta naught was 0, then 5% of the time our samples would just so happen, we would think that it was beyond the significance level, and we would incorrectly reject the null hypothesis, which would be a type 1 error. So we would incorrectly reject a null when it was true, and that would be a type 1 error, which is right here. Okay. Now, depending on say there is a difference, and I believe there actually is a difference, then the next question we have is, what is that actual difference? Is it $30 more that you would offer a friend? Is it $50 more, 70, something like that? Or is it actually more than that, and our sample was just on the low end? We don't know. So let's say on average you would offer a friend $50 more. So I'm putting the actual difference between the means of $50 on average you would offer a friend more for that camera. Then this is going to be the power of the test, which is kind of cool. So our significance level means we would have to have a sample mean, the difference in the means has to be larger than this critical value right here, or significance level is the best way of putting it. And anything that was lower than that would have been a type 2 error, because now it's not, there really is a difference. We said it was a $50 difference. But if we failed to detect that, if we didn't reach this significance level, then we would have falsely failed to reject the null, which would have been a type 2 error, right? So we got two different types of errors. We got our false positives, which is when it's actually, there is no difference and we accidentally think there is. And then we have a false negative, which is when we fail to detect something, right? Both types of errors are bad depending on the context. One might be worse than the other depending on the perspective of the person involved and which side of the whole situation. So one thing that I do want to add here is that we're actually not using a normal model with degrees of freedom of infinity, because we're dealing with sampling means. Our degrees of freedom, which came from the calculator, is going to be here. So notice how these are going to be extended out a little bit. That's because the model is actually a little flatter and a little bit wider. So when we do our alpha levels for 5%, it's actually going to be moving off just a little bit. So what happens is we actually have a slightly less powerful test because we're sampling with means, because we had to adjust for the fact that we are measuring their standard deviations of the samples from the sample mean, not from the population mean. And they're always going to show less variation when we compare the deviations from their own mean, the sample's mean, compared to the population's mean. That's just how that stuff works. So because of that, it causes us to have to change our models to correct for that when we're dividing by n-1 the degrees of freedom, instead of dividing by n when we have the whole population. Anyway, kind of cool stuff. I enjoy it. So that's pretty much it. I'm pretty sure, yeah. Yeah, so we can create a confidence interval now that we've said that there is a difference and it's a statistically significant difference. The next question is what do we think the true difference between those two means would be? So to do that, we create a confidence interval. It's the same math, except now we take the difference which we observed, which was a 70.5, and we add or subtract the critical value. So if we want, what level of confidence? Looks like we're doing 95% confidence, because that would be 2.5 on each tail. With this degree of freedom, which came from the calculator, right? That gives us a critical value that we'd have to do, meaning we have to go out 2.33 standard deviations. So then we multiply our standard errors here, so that times that value there, and we add and subtract the margin of error to our critical value, or sorry, the difference between the means that we found from our samples, which isn't quite our delta knot because it's not the hypothesized value, but you get it. Anyway, which gives us anywhere from, we believe the true difference between how much more you would pay a friend than a stranger is anywhere from $27 for this camera to $114 essentially. And that would be, so we would say we're 95% confident that the true difference in the proportion how much more you would pay a friend for this camera than a stranger is anywhere from $27 to $114. So conclusions, our p-value is less than 1%, less than any reasonable alpha level, and so we would have enough evidence, or our observed difference in our samples would be statistically significant in order for us to be able to reject the null hypothesis in favor of the alternative. So we believe there is a difference. We believe that the difference, our sample was 70.5. That's what our sample showed. So that's our best estimate. We think it's centered at that, but we think the true proportion might be anywhere between $27 more to $114 more with 95% confidence. Another way of writing the confidence interval. And keep in mind, there were not equal variations between the two, so it was not appropriate to pull this data together. When you put it in your calculator, it'll ask you if you want to pull it. So if we go to stat test, we're going to do a 2-sample t-test. Yeah, see on the very bottom here, it says pull yes or no. It's when we're doing proportions, you should always pull, because we know their variations are going to be equal because they're tied to the binomial model, so it's predictable, right? But when we're dealing with means, we should default to no, where we don't pull unless we believe their variations are the same. And keep in mind, the benefits we get from when they have equal variations is very minute, and so there's not a whole lot of benefit in pulling in the first place. So we just would say no, and we could fill in the rest of this information if we wanted to. Do we want to? Yeah, sure. So let me go back to the original one where I had all the stuff put out. So I think we're pretty much done. So if you just want to move on to the assignment, you have my permission. If not, stick around. We'll do this part together. All right. So the average that we got from our first sample, and I'm going to put the first one friend because that was the bigger value that we got, was 281.9. You also could just put it in data if you want to put those in for list 1 and list 2. So that's another way you can do it as well. So anyway, but I have the summary statistics, so I'm going to use them. 18.3. The sample size for the sample 1 was 8. The mean for the stranger was 211.4. Standard deviation for that was 26.4. You're asking, how can he see through the calculator? Well, it's the same value right there. Anyway, sample size for that one was 7. And we hypothesized that they were, that the difference was, it was just that it was different. So otherwise we would say the first one was bigger than the second one because the first one, our first sample we put in was the friend. So would we offer a friend more than someone who's not a friend? It should ask us our difference, hypothesize difference, but I guess not. Okay, so yeah, it is just assuming that our null hypothesis is that it's delta naught is 0, which is interesting. So if we wanted to hypothesize, say someone said that you would offer a friend $20 more, and we were saying BS, we think it would be more than $20, then our hypothesized difference would be 20 instead of just saying that they were greater than or less than. So that's interesting. They don't really even give you the option to do that on this. Okay, so calculate, and p-value 6.6%, which is exactly what we got. 3.77 standard deviations above the mean for t. Degrees of freedom, that came from that nasty formula, but again, when we put this in the calculator, it gives it to us, and then just restates all of our summary statistics. Yeah, and we're good. I think if I did a confidence interval, I guess I'll go ahead and show that real quick too. So if we're doing a 2-sample, not a z interval. The reason we're not doing a z interval because that's a normal curve, right? Remember, ours are based on Gosset's distributions because we don't have because we're sampling means. Confidence level, we'll do 95, and we should get the exact same. Again, we're not going to pull because they don't have equal variance, which they rarely ever do. And that should be, yeah, from $27 to, that might be a little different than what I showed. It looks like it was a little different. Yeah, 27.9. That's probably a typo. Yeah, 27.02 to 13.98. Okay, so slightly different than what I got. Might have had some rounding error whenever I put it in here. But yeah, that would be correct. Okay, cool. So I believe that's everything I asked you to do on the assignment. So just work on the last, the 4 problems on the back side. Keep in mind the odd problems are in the back of the book. And 23 minutes, that was quick. So you could have even bailed out even sooner. So I'll see you guys later.